All right, welcome back, everyone. We're back for another episode today. Hopefully, everyone had a great New Year. You know, as they say, New Year, new me. Although we always fall short of our New Year's resolutions, but maybe this year you'll be able to hold strong and keep it up for the entire year. Today, I'm really excited because I'm joined by Professor Daniele Leonori, who insisted on me calling him Daniel, so I will start calling him Daniel from now on. In any case, though, I'm really excited to have him on today. Really, just fascinating research. Really a lot of it with, radical chemistry. As someone who kind of is an editorial board member for Synthesis Workshop, your work for radical chemistry in reviews are brought up many times as citations for radical chemistry. And so we're definitely going to, talk about that in the future. He's a professor at, I got to pull up the full name, but I know it's RWTH Aachen University. It's on the west coast of Germany, bordering, I think, Liechtenstein, maybe Luxembourg. No, the Netherlands.
Belgium and Netherlands.
Belgium and Netherlands, yep. So very excited to have him on today. So yeah, well, I guess, to get going here, I guess we'll introduce, Daniel. He definitely has a strong Italian accent. So, you grew up in Italy. I don't know if you want to maybe introduce yourself. Kind of like starting from like your background, and we can kind of go from there.
Yeah, great, thanks. Sure. So I grew up in Italy, in Perugia, close to Perugia, which is a city in the center. I studied there, MedChem really, and then I went to the UK for my PhD in Sheffield in organic synthesis, and then I went to Germany. I did 2 postdocs, 1 year in Aachen with Magnus Rueping, and the second one with Peter Seeberger at the Max Planck for Colloids and Interfaces in Berlin. And then I went back to the UK. I was for a couple of years the research officer of Verinder Agarwal at the University of Bristol. And then I started my independent career in Manchester in 2014. I've stayed there for 6 great years. And then in 2022, I started here in Aachen. And I'm really excited to be here in this podcast. Thanks for having me.
Yeah, of course. Yeah, so just kind of on your background a little bit, you mentioned that you kind of grew up in the center of Italy. Kind of coming up, I mean, were you always interested in STEM or anything like that? Or did you have any particular hobbies kind of coming up? Maybe like through like the junior high school area? Or like, what were some things that, really interested you kind of coming up?
Yeah, so I've always enjoyed science. So my mom is a pharmacist and my dad is a doctor. So I was always interested into this kind of topics, mostly because of the conversations that they were having at home and an interest in their jobs. And I didn't really have any hobbies when I was a kid, apart from playing guitar. I was part of a little rock band. I wasn't really good, so I stopped very early on. And then, yes.
Did you at least have a rock band name? Did you have a name for your band? Or is it?
Yeah, it wasn't a particularly inspiring one, so I'm not gonna mention it. I'm kind of embarrassed.
That's fair. Do you keep up with guitar at all today, or is it just something you kind of did? It was kind of just a phase when you were kind of younger with music.
It's really interesting because I really loved it, and then I started to realize I was really bad at it. So I just couldn't play it at some point anymore, and I decided to stop and do other things. Yeah, but I love to watch YouTube music videos, and I still follow, the guitar heroes I had when I was a teenager.
Yeah. It's real quick. I'm pulling up a map of Italy because I got to get my bearings a little bit here. Because I pay attention to like European football, so I'm very familiar with like Juventus from Turin. I'm a big AC Milan fan, so Milan, Inter Milan. You're a big AC Milan fan?
Mm-hmm.
Oh my God, let's go! That's so clutch. I could pull it. Maybe I have a 2006 Ricardo Kaká Champions League jersey in my closet right now.
Wow, that's fantastic!
I wear that one. I wear that one proudly. Maybe I can actually let me show it out. I'll pull it out real quick. It's really cool. 1 second.
Yes.
Yeah. Very cool. Definitely, it's like one of my favorites. Yep. But
yes, was one of the best players. Kaká was incredible. Yeah.
Yeah, definitely one of my prized jerseys. I think he
Yes, I
won.
wish I had it.
I think he won the Ballon d'Or that year. I think he
Probably,
did.
yeah.
Yeah. So anyway, yeah. So Italian football is definitely something I've grown up watching, especially that run to the Champions League final, which they won, by the way.
Yeah.
But I'm just so where'd you said you grew up kind of central Italy, right? I'm trying to find
Yeah,
a
Perugia, close to
Perugia.
in a little village close by. Yeah,
Perugia. Yeah, my Italian's
it's
not
between Rome and Florence, right in the middle of the
Rome.
country.
Okay, I got you. Oh, I see. Okay. Yeah, so kind of coming out from Italy. I mean, are there things maybe in Italy that obviously you have like the touristy more attractions, right? You have like which are great, by the way. The Colosseum.
Yeah.
You know, there's a lot of like historical places there in Italy, but are there places maybe that if one were to visit Italy to kind of go check out that is really, whether it's cuisine or cultural, historically important, that a lot of people may not know about, that are kind of outside of the
Mm. Well,
touristy
I would
places.
say the region where I come from, Umbria, it's a little bit untouristic compared to, for example, Tuscany or the area close to Bologna or to Venice or Riviera or this kind of areas. And I think it's an interesting place because um, it's still quite genuine in the way it looks and in the way that people cook and all this kind of stuff. So an interesting place to see. And there's a lot of beautiful cities like Perugia, Foligno, Spoleto. These ones are very beautiful places with a lot of historical backgrounds, the Renaissance and all these things. I would say Sardinia is a great place to visit as well. It's very beautiful if you like the sea and this kind of things. But also, it's a very interesting cultural heritage, which was called the Nuragic culture that goes down really, a long, long time ago, and with very fascinating structures and type of, artistic things. So that's a very beautiful place as well, with a lot of cultures went by Sardinia. And so on the west, for example, they speak Catalan almost. So it's a very interesting place. It's difficult,
Yeah.
because Italy is a beautiful country and it's a lot of great places, and it's very difficult to find one or an area that really has not been found already by tourists or that is not famous for something.
Right.
And I really like it, of course.
Yeah. I think it's definitely a country that I definitely want to go visit.
Mm,
I have a buddy of mine. He's half Italian,
okay.
half Ethiopian, but on his Italian side, he grew up in Udinese, so they're really the northeast part of Italy. And obviously, if you go to like Udinese northeast, you have Venice, Milan, and then
Mm,
you go. That's kind of the north part. But then as you start going down, like it really is, it's extremely different. Maybe both like landscape wise, but also
yes.
huge. So there really is a wide variety of, from what I understand, anyways, of Italian culture. So
Yeah,
definitely is
because
a very
Italy is a relatively, it's a very old country, but relatively new one because it was a lot of different countries. You had the one from the north, then you had the church in the center. I'm struggling to find an English way to call them because I'm just familiar with the Italian names. But so they have their own influences, their own artistic developments, their own architecture. So they're very different. And of course, the landscape is completely different. If you go from the north, then you have Pianura Padana, which is very flat. Then you go to the hills that you had around the center of Italy. So it's
yeah.
it's a very diverse place.
Now, so before attending the University of Sheffield for your
Mm.
PhD, did you do your undergrad also in Italy as well, or did you kind of travel outside to do your undergraduate degree?
No, I studied in Perugia,
Perugia, okay.
and yeah, so I did my master degree there, and then I worked for 1 year in a little pharmaceutical company that is on the outskirts of Perugia because I was trying to understand where to go and what to do, and then I
Mhm.
went to the UK.
Okay. So I think it's an interesting discussion point then. So, you got your master's degree, kind of stayed
Mm.
around. I got an industry job in a pharmacy company, right? Is that pharmacy yep. And then, but then you decided to, move to the UK and pursue a PhD. So I'm kind of curious to hear a little bit about that. Like, what were some of the thoughts leading into kind of leaving that behind and going to do a PhD?
Well, I mean, during my master, I kind of, I decided that that's what I wanted to do. I wanted to do a PhD. I wanted to continue to work in science. And by talking to a lot of other people, it was clear, that doing a PhD was the right move if you wanted to pursue a career either in academia or in industry. So, and then I've been always fascinated by staying, outside. A lot of my friends did Erasmus, which is a scheme that we have in European universities, whereby as part of your master degree, you end up spending 1 year in another university in another country. And I didn't do that. But everyone was coming back and they were so excited about, these experiences abroad. And I was seeing that they were actually different when they were coming back. Like they kind of developed in a different way, from me. And so I felt that was the right move to leave my comfort zone. And I was always been interested by the UK because it seemed, a very vibrant place, and Sheffield gave me an opportunity, and I'm very grateful for that.
Yeah. So how did the opportunity arise to go to Sheffield? Like, what was the draw to go to Sheffield? I don't know. Because Sheffield's kind of, I mean, it's not really one of the cities, I would say it's not really in the top 7 cities that people would, when they think of the UK, to go visit or go do a PhD anyway. So, what was the opportunity to go do it at Sheffield?
I'm going to be brutally honest on this. So I didn't have many options, really.
Yeah.
I applied for a lot of PhD studentships that were coming up. And I guess just my profile wasn't attractive enough. So I just didn't get a lot of calls for interviews. Actually, I had one from Nottingham and one from Sheffield. I didn't apply really to universities to other countries. I just applied in England. And I went for the interview in Sheffield. I really liked the place. I really liked my boss. And I just went there immediately. And but retrospectively, it was the right move. Also because, as you said, it's not one of the cities where you would go in England, but it's a really interesting place because it's very close to a national park, which is called the Peak District. And now it's a really beautiful area. So I had a lot of fun there going around in all these countrysides, and and it's not too far from Manchester and other big cities, so you can have fun.
So a little bit, I mean, Sheffield, I mean, I keep bringing up football because the only thing, it's kind of what it brings me to, I mean, Sheffield right now, unfortunately right now they're in the bottom of the Premier League, but the Blades are, an established, championship level football club. So I mean, it's definitely a, working class city. And like you mentioned, the Peak District National Park is also right there. So it's far from like uninspiring. It's far from that. It's certainly things to do there. I want to thank you for sharing that. Like, you not getting a lot of PhD, I guess PhD ships or PhD opportunities,
studentships, we call them.
Studentships, because I know right now, as I kind of see on Chem Twitter, I mean, I know personally a few students that they didn't get accepted for like 30 PhD studentships. So, it's quite difficult, and like, it's a bit unfortunate it is that way, but that shouldn't discourage you from doing that. And, the best opportunities are the ones that maybe you didn't really set out to at first. I mean, like you mentioned, University of Sheffield is probably one of the best things for you. And we'll definitely talk about that as why that is. But, I think, like I mentioned, if you don't get those first, your highest rankings, or the ones you really want to go to, it doesn't mean that there's not opportunities elsewhere. So you're at the University of Sheffield doing your PhD, and I think, let me pull this up real quick. You were with Professor Iain Coldham, I think, right? So, what kind of drew you to his group, and what were you working on as a graduate student?
Well, so when I went to the interview, I don't know, something just clicked with me, and I just found him to be a very nice person, and he was very kind when he was talking to me, and very genuine as well. And the project that he proposed me was something that I never heard of, which was, asymmetric synthesis of organolithium with organolithium compounds using thermodynamic resolution processes. So I just had no idea about that. But when he discussed the project, it was so easy to understand him and to follow him, and I thought I can learn something here.
Mm.
And so then I was very excited, and we started to discuss quickly about the project, and I asked him questions, and I saw that he was replying to me in a very nice way and taking into account what I was saying, even if I knew that I wasn't understanding much of the chemistry. And it just felt like a great person to work for. So then I decided to go there, and then I did a lot of asymmetric synthesis, a lot of physical organic chemistry. It was tough, especially at the beginning, because I studied pharmaceutical chemistry, so I didn't have necessarily a strong background in physical chemistry, physical organic chemistry, and all these kind of aspects, and I had to catch up quickly. But he was a great supervisor, and he really helped me, and then it was a great experience.
Mm. Yeah, I guess getting those, it's kind of an interesting dynamic is that when you're pitched a project as like a first year,
Mm.
it's kind of funny because like there's like a lot of big words and it's like wow like I don't like yeah I remember the feeling of graduating from undergrad and thinking like I was on top of the world and like I got that grad school. I was like wait, I don't even know anything yet. And so I always find that funny. So getting pitched a project, there's kind of like an ignorance is bliss kind of thing where it's like wow, and then like the way that they pitch the project, it all sounds really fascinating. And more often than not, like well, you know it depends, I guess, but like picking up those projects and being able to actually explore them and working well with your PI is definitely an awesome experience. So yeah, I think that's really cool. So a lot of asymmetric synthesis. Um, yeah, I can't imagine that was easy though. So like, what skills in particular or knowledge you kind of didn't have that you really had to pick up quickly during like let's say the first few early years or early months as a graduate student?
Yeah, so I didn't have a really strong background in organic chemistry in general, if you think in terms of mechanistic organic chemistry.
Mm.
So I remember going to the first group meetings where they were doing problem sessions, and just this feeling of I'm not understanding what they're talking about. So I just really needed to. So I was really good, I think, in terms of practical skills in the lab, and I had a fair good idea on how to plan synthesis, but I had no idea, let's say, on mechanisms and aspects of reactivity and all these concepts. So that is something that I had to restudy essentially quickly. And Ian, my PhD supervisor, was really good because he's a great teacher, and he really explained me a lot of these things. I mean, I think he saw that I was putting a lot of efforts into trying to catch up, and he wanted to help me. And so that was really exciting because sometimes we just had discussion about undergrads kind of topics, not just about my project. And that was really cool. I'm really grateful with him for that, for the time that he spent with me for this. But
Yeah.
I didn't know much about in terms of aspects of, for example, thermodynamics and kinetics, or aspects related to conformational analysis and all these aspects. And these ones were the things that it took me my entire PhD, to understand them well. But then at the end, I felt, no, I learned a lot of stuff, and I think I know the usual concepts that a synthetic chemistry PhD student is exposed to.
Mm. Yeah. Yeah, I definitely I hear that. I think learning those mechanistic details. I think it's interesting because like the first semester when you take like an organic reactions or an organic synthesis
Mm.
course, you definitely get exposed to, at least I did, those conformational analysis, understanding thermodynamics and kinetics. Like you see them, but after it's done, you kind of forget about it unless you're doing it day in day out. Like you kind of have to just, and it's a grind. I mean,
Mm.
to become like, I mean, expert or really knowledgeable in that field, you have to be doing it basically almost every day, a little bit every day. And it definitely helps to be doing experiments to help you facilitate that as well. So I hear that. Now, after your PhD at the University of Sheffield, you go on to do your one of your first postdocs at Aachen, which is where you are now, with Magnus Rueping. Now, at this point in your career, was being a professor something you'd really thought about, or was it kind of just a natural progression because, maybe the job market wasn't right yet, or so like what were kind of the decisions leading into doing that first postdoc?
So I wanted to be an academic. I knew that. So I was trying to make the right steps to pursue that kind of career. I was open to a job in industry. 2010 and 2011 were difficult years because that's when there was a huge crash, especially in Europe in the pharmaceutical sector. So a lot of pharmaceutical sites closed, a lot of people made redundant. So there weren't many jobs. The competition was huge. So I never even applied to an industrial job. So I just continued to move forward for the academic route. And that's why I went to Aachen, because I wanted to do something completely different. I wanted to work on organocatalysis. And Magnus Rueping was one of the rising stars that initiated the use of bronzed acids in asymmetric synthesis. And I just wanted to learn from him how to do that chemistry.
Yeah. So during your PhD, though, were the thoughts of becoming a professor kind of creeping into your mind? Because, I don't know if you'd ever, like, even like when you'd finish your undergrad, if you ever thought about becoming a professor, but then you do your PhD, maybe like those kind of thoughts come into your mind. So was it kind of during your PhD that you really wanted to pursue academia as a career?
Yeah, I think so. I think so. I don't remember very well what I was thinking, because I don't think I had any clear thoughts at the time of what the future would have been. But I knew it would have been chemistry, and I knew it would have been doing research. I think when I was a PhD student, I was still considering very much industry. And then towards the end is when I decided that I would have liked to be an academic.
Yeah, that makes sense. I find that to be the case a lot of times, is that there aren't really many people that I know that are like, yeah, I've been wanted to be a professor since like undergrad. It's more like you kind of just comes natural, I guess. Yeah. So
I think it's also because when you are an undergrad, I was perceiving my professors as teachers, not as researchers. Is when I did my PhD, then I realized being an academic actually is about being a good researcher and a good teacher at the same time. So there's an aspect of it that I learned when I was a PhD student, which means managing a research group and writing papers and all these aspects.
Yeah, that makes sense. When I was undergrad, I didn't really see my PI as like a researcher. So I definitely understand that. That's actually a good point that you say it. Okay. So in any case, you're doing asymmetric bronzed acid organocatalysis with Professor Rueping. You're there. I think, this is I'm actually not really familiar with this field too much. I do know that Professor Benjamin List has asymmetric bronzed catalysis or bronzed bases. I think he also kind of does bronzed acids. And he's recently published on that. So maybe I don't know. Maybe you could tell us a little about the early stages of that field, right? Because that was kind of like, I guess when you were working on it, that was kind of it's kind of a newer thing. So I don't know if you want to just tell us a little bit about the science of that.
Yeah, so Magnus and Ben, they started more or less at the same time working on this area. Ben List, of course, started earlier because when he started, he pioneered the field of enamine catalysis with proline and these different types of reactivity. And then other people like Terada from Japan started to publish this concept of having a proton and a chiral counterion, and the counterion was controlling the stereoselectivity of these kind of reactions, which, if you think about it, is really exciting because it's not a covalent interaction of a Lewis acid with a chiral ligand. There's a proton the protonates something, and then you have a chiral counter ion nearby that influences this type of reactivity. And at the beginning was used in aldol reactions and in these kind of things. But what got really interested, so I got really interested in Magnus chemistry because he kind of showed that he was protonating, for example, quinolines or isoquinolines or pyridines, and then he was mimicking the reaction of enzymes of the NAD reductases and these kind of things with different cofactors. And then he was doing asymmetric hydrogenation reactions of quinolines, pyridines, and these kind of things. And I just felt that was a very interesting, a very creative way of tackling that kind of chemistry. I just wanted to learn how. I think when I decided to go to work for him, my desire was not really to do that chemistry, but to understand how he arrived to that conclusion, which thought process he got, to do that kind of chemistry, because I thought it was really creative.
Yeah, that is really creative. I can't think of a scenario. Again, I'm only a third year, so I don't know how I would really get there. But to do asymmetric bronzite acid catalysis using basically a chiral ion pair, right? That's basically what it's doing. Is super creative. At the end of the day, it's just super creative. And when I see those ChemDraw figures, they're really cool to look at. Having those those chiral backbones to control the I guess enantiomer selectivity, or is it would it be
selectivity?
Enantiomer selectivity, right? So yeah, that's really cool. And so all right, so during your time there as a postdoc, did you have any contributions, or kind of what was kind of your takeaway during your period there as a postdoc?
My takeaway was that this is a very difficult field of research. So all the things that I tried failed miserably. So I didn't manage to get anything to work in the way that we would have wanted to. And then something that was very exciting about the time was that I joined Magnus group when he started to shift his research program, and he started to look into photoredox catalysis. So this was the time when photoredox really started, when Macmillan, Corey Stephenson, and Tashi Kuhn and Magnus really started to publish in this kind of area. So then I saw essentially the group starting to work in a different project and different research line, and out switch completely, let's say, the research questions and all that kind of stuff. And that was really good, and I managed to jump on that area and work a little bit on photoredox, and that was very rewarding, because it was very new and very exciting, very different. These reactions with the light bulbs, we were doing them in a very let's say unsophisticated way at that time, and I think this is what I really learned, and then I followed photoredox and photochemistry for the years, and that's where I decided to work on when I started in Manchester.
Yes. So, moving forward then, so, after your first postdoc, you then moved to the Max Planck Institute with Professor Peter Seeberger. A second postdoc, moving to, over to the Max Planck, what were you working on over at Max Planck, and, what were, why move over to the Max Planck Institute for a second postdoc?
So at the Max Planck, I was doing carbohydrate synthesis. So I was doing de novo synthesis of monosaccharides. And so Peter Seeberger is a person that I think it was one of the first seminars that I have seen when I was at the University of Sheffield as a first-year PhD student. And it just blew my mind, because he was making this machine to assemble these hugely complex polysaccharides, and then he was making vaccines, was treating malaria, was building companies, and it's one of these figures that then I kept following. I was always reading his papers, and when I was a postdoc, I started to think that it would have been cool to learn a little bit how to use chemistry to solve biological problems. And I decided to give it a shot and see how it would have been to work for this, hugely complex, working on these hugely complex questions on making vaccines and, look at these complex saccharides, making machines to make the molecules. I didn't have a chance to do all of this, but it was really cool to see how his group does it effectively.
Yeah. So one thing I'm kind of picking up on is you really had a diverse skill set. I mean, by the end of, I guess, your second postdoc, I mean, between what you've done at Sheffield, then doing, at least attempting to do, like bronzed acid organocatalysis, asymmetric catalysis, but also some photo redox, and then finally, you're doing not machine learning, but making vaccines, but using robotics to do the chemistry. Is that what it was, or
that would have been
monosaccharides?
Yes, monosaccharides. If I would have managed to find a really effective way of making these building blocks and found a very good way of using them in glycosylation reactions, then the next challenge would have been to translate the chemistry into robotics. But I didn't manage to do that.
Yeah, it sounds like a lot for one person to get through. But in any case, it sounded like a very admirable goal at first, but I'm sure there was a lot of hiccups trying to make monosaccharides. But in any case, I mean, you had a very diverse skill set coming out of especially out of that second postdoc, which I'm sure definitely helped you into kind of your career now, those skills. So I definitely want to transition now into your research. So like you mentioned, you first started at the University of Manchester, but now you're at is it RWTH Aachen University, like I mentioned, kind of on the west coast of Germany there. And you really have a really diverse area of research. I mean, you're probably most known for your halogen-atom transfer reactions and those type of things. But you also do nitrogen radicals, cobalt chemistry, cobalt desaturation, and also doing now boryl radicals. So I know radicals are kind of like radical chemistry is certainly something you're very familiar with. Perhaps we can start with your early years. Well, maybe the early years of research and when you first came in as a professor. What were your initial research interests, and have any of them early ideas kind of managed to facilitate themselves into today, or how has it kind of changed over time? So
so when I started in Manchester, I wrote few proposals. So these ones were again I would say still relatively the early stages of photo redox, and I saw a window of opportunity because everyone was doing carbon radicals, and I felt, what about an heteroatom radical? And then I saw the beautiful work of people like Samir Zard and Derek Barton that back in the days looked at these nitrogen radicals, and I felt maybe we can re-innovate a bit this chemistry and make it a little bit more modern by using this new technique. And maybe if the techniques allow us to make this radical in a better way, maybe we can explore them in different types of reactivity patterns and amplify, the synthetic potentials that they can offer. So this is what I wanted to do in Manchester, and this is what I did for the first 3 years. So the first 3 years, my group was very small. It was me and the very first year was me and one PhD student, and then I got other 2 PhD students. So we were 3 or 4 people. So we were just working on this nitrogen radical chemistry. And then I managed to get a bit more funding, and then I always felt I was getting a bit bored about what I was doing, and it was time to move on and then change topic. I didn't want to remain trapped in one research line, and I wanted to explore new things and new concepts, and that led to a lot of different things like the cobalt catalysis first, and then the halogen-atom transfer. Many of these projects came by mistake, or was the intuition of a postdoc, or was just something that we felt we could have done. Not necessarily, we didn't anticipate, where to take it or where to go with it. But I really started with the nitrogen radicals, just trying to develop their chemistry at the very early start.
Yeah, I was kind of going through your publication list. A lot of it is the nitrogen radical stuff. Yeah. We can definitely maybe start with the nitrogen radical stuff. I'm not really, perhaps if you want to give us a little bit of insight into the thought process for utilizing nitrogen radicals to do various transformations. I don't know if there's a few that kind of stick out in mind, but if you want to tell us a little bit about kind of the synthetic utility of the nitrogen radical, and I guess also too, like where it kind of came from, like where was there precedent for it, or where this idea of utilizing a nitrogen radical kind of came from.
So, I mean, so I was interested by the idea that the nitrogen is a nucleophile or a base, essentially, in organic chemistry. So you tend to use it in these kind of concepts. The nitrogen radicals add a different type of reactivity. I didn't appreciate that much that by generating a nitrogen radical, you effectively switch the polarity of the nitrogen. You're almost dealing with electrophilic species. But I was interested by the fact that they could essentially react as electrophiles. So then you could have a lot of different retrosynthetic disconnections, compared to the normal way that you would use when you want to form a carbon-nitrogen bond. And then, of course, there are all these classical reactions like the Hofmann-Löffler-Freytag process that when you look at it, it looks like an incredible way to make a pyrrolidins, because you take an alkyl chain and you do CH. It looks almost like you're doing CH activation and you form a carbon-nitrogen bond across a carbon-nitrogen bond. And that's how you form an heterocycle of 5-member ring with a nitrogen and, with a nitrogen atom inside. And I just felt that people weren't using this concept and that people were assembling carbon-nitrogen bonds in different ways. And I was curious to see why was that, and because to me there was a lot of potential. And then, of course, when I started to read the literature, I realized that people have done incredible work in the area in the 70s and in the 80s. People like Samirzad, for example, in France. But still, when I was looking at the reaction conditions, I felt that maybe the reasons that people weren't really using these methods was that they were using tough reaction conditions with really toxic chemicals like tributyltin hydrides or AIBN, which is an explosive initiator for radical reactions. And then when I started in Manchester, I just wanted to see if I could make them just with visible light, okay? Just because I had this idea of using visible light. And then when I started to work on this topic, I started to learn really about photo redox, and then I started to appreciate the advantages that these kind of methods could give you in the way that you could design, let's say, cascade reactions with multiple redox events. So then forming carbon-nitrogen bond using nitrogen radical became almost like as an excuse to generate other types of bonds, okay? And then we could diverge this chemistry in a lot of different ways. But that didn't come at the beginning. That came by understanding a little bit this kind of reactivity when we were working on it. And then from there we started to, and that really redefined my understanding of radical chemistry that I didn't really have when I started in Manchester. This concept of radical philicity, polar effects in radical reactions. And then that has really changed my approach to this kind of chemistry and led to halogen-atom transfer, the boryl radicals, the nitroarenes, and all the other projects that we've been working on.
Yeah. I guess a quick question. This is kind of a quick aside then, because it kind of goes hand in hand with your research. But the way, I don't really know how important it is, but the way that we teach radicals chemistry at an undergrad level is kind of really disingenuous, I think. I don't really know how to fix that. I will say that, like, maybe at an undergraduate organic chemistry level, the level of detail that we've gotten to at this point with radical chemistry is just far beyond maybe their understanding. But I think it does a disservice, though, by the time, like, let's say, though, you have some students that go on to do a PhD studentship, they already have this preconceived notion that, like, radical bad. Like, it's kind of like the only thing they really, not bad, but, like, it's really reactive. And that's probably true, but, like, I feel like it's kind of always in a negative connotation. So, rethinking, radical chemistry is something I think that the community in general is moving to, like, really kind of understanding the nuances of, like you mentioned, the radical philicity, the kinetics and thermodynamics of the radical. I don't know, but I just don't know if that's worth implementing at an undergraduate level. I don't know if that should really be. I'm curious to hear your thoughts on that. Like, if there's a way to maybe think about radical chemistry kind of at a younger level.
Yeah, so I think you're absolutely right. I think we do need to bring this up in in the undergrad courses, because now it's so important, radical chemistry, especially with developments like the reactions with the metals and all that kind of stuff. So I think it's important to give that kind of perspective to the students. So I do it. I teach a course here in Aachen. Also, I was also teaching a course in Manchester where I introduce the students to all this concept, and I keep it very simple and maybe too simple, but I explain them polar effects in radical reactions, kinetics and thermodynamics, and all these things. I think this will be difficult until someone writes a book for the undergrads that discusses this, because we don't have a book. I think that's the real problem. And these are difficult topics because I would say a cycle addition reactions, it's easier to teach to an undergrad, or a cross coupling, it's easier to teach to an undergrad because you can write a nice catalytic cycle, or you can show some nice frontier molecular orbitals, and everything makes sense and is translatable. I think with radical it's a bit more difficult because there's so many variables that you need to take into account, which can make it a bit more tricky. But I think someone will have to write the book at some point, because we need to pass these concepts to the new generation of undergrad students.
Yeah, I think that's a great point. I think it's somehow, hopefully someone can do it. Like basically like consolidating all these concepts and distilling it down into a book that an undergraduate can understand is kind of what's missing, I think. Like you mentioned, it's very understanding radical chemistry for each element and the polar effects. Like it's super nuanced. So I don't know how you do it. I would look forward to reading about it if someone's doing in the future. That's definitely not an easy. That's definitely not an easy challenge. No. It is what it is for now, but hopefully someone could tackle that in the future.
Yeah.
So like I mentioned, you do a lot of radical chemistry. I know another area of research that people probably know you for is definitely the halogen-atom transfer. I recently read your I don't know if this is not too long ago. I read your review on the applications of halogen-atom transfer and kind of how do you generate like carbon radicals. If you are interested in how you generate carbon radicals, I definitely recommend checking out that review. Super useful. That gets cited a lot because it is just straightforward and right to the point, which is much appreciated. But this idea of halogen-atom transfer, though, for your transformations, I don't know if you want to tell us a little bit about that and what it is really, and how you guys have used it to do various applications.
Yeah. So the genesis of the project really has been that the halides, especially the alkyl halides, are super important building blocks in organic synthesis. Of course, you use them a lot in transition metal catalysis because metals can insert into carbon-halogen bond through oxidative addition processes. The sp3 carbon-halogen bonds are a little bit more difficult because then once you form the transition metal complex, that can undergo a bit hydride elimination. This is a very, very general way of looking at it. Of course, in photoredox and in radical chemistry, generating a carbon radical from an halide is a little bit difficult by single electron transfer, because if you need to inject an electron into the species, then you're fighting a reduction potentials, which is very negative. So that means it's difficult to reduce this kind of species. And there's a lot of people that are trying to develop some really good photoredox catalysts. They're very strong once they're in the excited state, and they can reduce the species very well. I was always interested by the fact that still now, one of the best way of generating carbon radical is this concept of halogen-atom transfer, which is the oldest way of generating carbon radicals from the halide, which means you use tin or silicon radicals, and tin and silicon radicals are just great at abstracting the halogen. Okay, and this is something that, for example, they do teach us in undergrad's radical chemistry, the fact that tin halogen bonds are really strong. They don't teach us the polar effects, which are the key aspect, but we have this kind of concept. in our mind when we think about radical chemistry. And because of all the emphasis on polar effects on nitrogen radicals, I was always thinking in terms of polar effects and all these radical stabilizations and, stabilizing positive charges and negative charges in the transition state of these reactions. And then from there essentially came this idea of, what kind of radical could you use that is not tin and silicon but can stabilize an incoming positive charge? And we made all sorts of mistakes when we were trying to develop this chemistry because we didn't design it with these alpha nitrogen radicals, which is what we have published. We designed other systems. We were looking at metallo radicals, but then eventually we managed to arrive to that idea and to that concept. And that has been very useful for me and for my group because it was something brand new for us. And it allowed us to relook at chemistry, simple chemistry that was difficult to do in a very effective way. And I think people liked it because it was so simple and a lot of people could use it. It was reproducible. A lot of pharmaceutical companies contacted us and they were using it and they wanted to know tricks and tips on how to tackle that kind of chemistry. And then it really opened up a lot of opportunities because it was kind of a proof, that these polar effects were important in this kind of reactions. And then we knew what to do next and how to expand that kind of concept and how to use it in different scenarios, like in combination with copper, in combination with cobalt.
Yeah, so I think an interesting maybe tidbit of information for people is maybe understanding why tin radical or using tin as a reagent is kind of hazardous. I think some people may not be aware of that.
Okay.
So I would say maybe for like even like an industrial process, like why would one? Because because like you said, using tin radicals to abstract like halogen to start the process is super like useful, and it works like pretty much all the time. So why would you not want to do that, let's say on an industrial scale, or like what are some of the issues with that?
Well, tin is, some of tin compounds can be very toxic. Not all of them. Okay, some are inert. Some are even used, for example, in boats when at the end of the season you need to give this paint to the boats to make sure that the algae don't form on the side of the boat. These are tin compounds essentially that you end up putting there. They're not all toxic, but the one that people tend to use for radical chemistry, like tributyl tin hydride, trimethyl tin hydride, and then the corresponding byproducts, once that you have formed the tin halogen bond, these ones are toxic, very, very toxic. And the problem is not just the toxicity, but you need to use a lot of those in many cases. And then you end up having a lot of waste and you need to deal with this waste in the appropriate ways. So in a lab, it's okay because you use a little bit of it. You make a tin waste box and then you give it to the chemistry store and they have to deal with it and they know what to do. But if you think about an industrial plant, you cannot use 400 kilos of tributyl tin hydride because then you are you have a problem that you need to find a way to get rid of this. So there are also aspects of sustainability. Yeah.
Mm-hmm. A quick question about, because I don't know the answer to this. If you wanted to use, let's say, AIBN and tin radicals for like to initiate your process, is it catalytic amounts, or do you have to have a stoichiometric amount of like per your, let's say, whatever your reactant is, or can you use catalytic amounts?
So AIBN is used always in substoichiometric amount because that is the initiator. So AIBN is a little bit problematic because it can be explosive. So, for example, when I was in the UK, in Manchester, we couldn't buy it. So you couldn't do that chemistry anymore because in the university, they just wouldn't allow you to have it in the lab. So tin species, that depends on the mechanism of the process. If the mechanism has a way of self-propagating, then you can get away with substoichiometric amounts of tin. In the majority of the cases, you need to keep adding these reagents to your reactions, and then you need to use a little bit more. Sometimes you need to use an excess. So let's say there is no one conditions. It depends from the process that you're trying to develop and the key mechanistic aspects.
Yeah, I guess on this halogen atom transfer discussion, I know moving forward, people obviously would love to get away from using tin, and so I know people have tried using phosphorus, and then, you guys tried using boron, boryl radicals. I know some people try using silicon, and obviously you can even combine photochemistry to these processes. Kind of in your opinion and what you've seen so far, is there really where's kind of the direction it's going for halogen atom transfer? Like, where is it kind of really the next, the community is really trying to take a look at to do these types of reactions? Is there kind of a one thing, or are there multiple, processes? Kind of, like to get your sense of where it's going with this.
So let's say that silicon radicals is a very well-established topic and a very well-established way of doing halogen atom transfer. So silicon reagents are the best one, in my opinion, if you're thinking in terms of reactivity. They offer you some incredible ways of generating radicals in combination, for example, with metals, and then you can do some really, really exciting processes with them. The drawback, or the drawbacks, in my opinion, of course, is the price of this kind of reagents. They're not really available in large scale, so they're great for small scale chemistry. I think they're not perfect for process chemistry on really large scale. But this is just my perception, and I'm not a process chemist, of course.
Sure.
I think there's a lot of opportunities in halogen atom transfer, in the way that I think we haven't found a reagent, that covers it all. So, for example, activating alkyl chlorides and aryl chlorides is very difficult. It's a really big problem, because these ones are the cheapest and the less toxic building blocks between all the halides that you can have. And I think the problem is that, for example, if I just can be very general, silicon radicals are great in terms of reactivity. Okay, they have the drawbacks that I have mentioned. The alpha nitrogen radicals that we have generated, for example, they're really good in terms of that you just use a simple amine like triethylamine, which is not a toxic chemical, very small molecular weight. The byproducts, you can distill them out, you can have it on very large scale, but they don't match the reactivity scope of silicon radicals. They address one aspect, but the other one is not addressed. So I think we don't have a reagent that you would say has a reactivity like the one of the silicon radicals, but addresses all the concerns in terms of price, molecular weight, and all these other things. So I think there is still an element of this. We still have problems in activating the chlorides, which is a big thing. And I think now, in my opinion, finding ways to activate fluorides would be very exciting, because the detoxification of persistent organofluorine compounds and all these kind of things. I think if one could do it with the simplicity of halogen atom transfer and radical chemistry, would be an interesting way of looking at that kind of problem.
Yeah.
But I think, there's a lot of people that work on halogen atom transfer. I think the research is more or less on using the sets of reagents and try to apply them. There's very few people that try to come up with new systems for activating these carbon-halogen bonds via ZAT, which is halogen atom transfer, is the acronym.
Yeah. I look forward to, I've noticed that, trying to generate, alkyl radicals from chlorine is just not really something really well established yet. And that would be, and from what I understand too, especially things like chlorobenzene or chlorinated like aromatics, those are the most common ones. I mean, bromine and iodine's aromatic compounds are actually much harder to come by. So if you can do that variation with chlorine, that would be super useful, particularly in the medchem world. And
exactly.
People that make so I look forward to that. I don't know, I think that'd be really interesting for, I assume people are working on that now. I can't imagine that people aren't trying to do that. So I look forward to that future. Transitioning a little bit to other parts of your research interest, one that I was really fascinated by, because I kind of come from the organometallic catalysis world, where generating, CN bonds using cross-coupling is something that I'm very familiar with. when I was taking a look at your publication list, I thought what was really interesting is kind of the desaturation approach, where you kind of condense on an amine, and then they're using cobalt desaturation to kind of get around that. I thought that was just super interesting. Kind of a what's the word I'm looking for? Like a alternative approach. Like it's kind of complementary research. And I thought that was really cool. Now it kind of brings up a broader picture of the cobalt desaturation. So I would love to hear like kind of the origin for this, like where, what were you guys doing? Because my impression is it wasn't like a big thought out plan. It just kind of happened, and I think it's super cool. So I don't know if you want to tell us a little bit about the cobalt desaturation. I think it's super interesting.
Yeah. I think the cobalt desaturations, I think the message that I learned from the process is that it's better to be lucky than to be smart, because it was a pure, let's say, accident that we discovered that kind of reactivity. So the first author of the Nature paper that we published on the chemistry, there was a postdoc in my group, Shashi. It was I don't know why he was. He always wanted to convert a ketone into an alpha beta unsaturated ketone. Okay, so and he came up with this idea of using cobalt. So he came up with this idea of forming an enamine, oxidizing the enamine, and then using cobalt to do a desaturation reaction, and then convert a ketone into an alpha beta unsaturated ketone. I think the luck was that he tried this reaction with cyclohexanone instead of cyclopentanone, and then the reaction didn't stop. It just continued. It formed a double bond, and then the alpha beta unsaturated ketone reacted again, was reoxidized again, and then cobalt did another desaturation, and then we got the aniline.
Wow.
And then when it just came to my office and he said, look, I've done these reactions, I formed an aniline. And then when he told me that, we understood immediately what was going on, and then we realized, okay, no one has ever done this. This is a really new way of making anilines. And then from there, we realized, the benefits that in some cases you can have in using a different type of approach, because you don't need to halogenate an aromatic, you can use a cyclohexanone. So it doesn't make cross-coupling worse, this kind of method. It's a complementary tool to make anilines. So it was a pure mistake. We just weren't looking for it. Yeah, I think, and this is something that I always say when I give a talk, I think the kind of reactivity was really there for someone to stumble across it, because I think Shashi, the very first reaction he tried was already 70%. So
wow.
I think it was the easiest project that we did in my lab, because the reactivity was definitely there from the beginning.
Yeah. I assume since then you've kind of done a little bit of like kind of understanding mechanistically what's going on here.
Yeah.
Desaturation, I mean, for some viewers, it's basically just, you have something that's saturated. So basically all your carbons are saturated with hydrogens, and if you want to desaturate it, you just kind of pluck out the hydrogens and you start forming double bonds. It's basically what it boils down to. So what is happening at the, do you have to kind of have a porphyrin type ligand, or, what's, I don't know what, kind of goes into this. Is it just a naked cobalt? I assume it's not, but
no, the ligand is crucial. So that is a cobaloxime. Okay. So these ones are very specific cobalt complexes that people have used a lot in the past in hydrogen evolution reactions. Okay, so we didn't invent them. We just used the tools that other people had already developed for other purposes. And they are really good at trapping carbon radicals. So this was known, that if you generate a carbon radical, cobalt will trap it very well. And then it was also known that if you have a cobalt bonded, let's say, to a carbon, then the bond is very weak and homolyzes very quickly, especially if you have light irradiation. And then the other thing that was known was that cobalt radicals, so cobalt-2 species, with this ligand, the cobaloxime essentially ligands, then they do very good at hydrogen atom transfer, and they form double bonds, which is a desaturation effectively. So all these things were known in the literature. I think people have never put them together to form an aromatic ring, okay, which is our contribution. But yeah, that's the aspects are known. Yes.
Okay. Yeah, that's. I think it's just the transformation itself is just super cool.
Thanks.
And It is very interesting how you guys kind of stumbled upon it. I love the honesty too, the serendipity of it. Like it's just kind of like, well, wow, we just did that, and it worked really well. So,
Yeah.
I love to hear those kind of things. Some other cool things that you guys are doing in your lab recently. What I was really fascinated by was doing like photo excited nitroarenes to basically make to cleave alkenes into or aldehydes or ketones. That is kind of, complementary to ozonolysis, basically. And I'd love to hear about that reaction. How where did that kind of come from? To do photoexcitation of nitroarenes, I think is, that excited state is super cool to look at. That 3+2 addition to the alkene is just super cool. It's super cool transformation. So I'd love to hear about kind of the inspiration for that reaction.
Yeah. So that is one of the first projects that I've designed when I was looking for an academic job. So at that time, I was looking very much at the old literature just to see if people had identified some unusual reactive intermediates or species that a strange type of reactivity once that they were in the excited state. So I found a very old paper from the 70s from De Mayo, which was a very prominent organic chemist from Canada. And he was the first one that really showed that by photoexcitation of nitrobenzene itself, he was doing these reactions. I don't remember exactly if it was which kind of olefins was using, if it was undecene or something like this, and he was observing these cleavages. So he wasn't observing the cleavages, he was observing the cycloaddition between the nitrobenzene to the olefin. And then he was saying that the product was just decomposing and he wasn't identifying the byproduct because it was a very impractical reaction done at -78 with the olefin as the solvent, with light at 250. It was very difficult to track, the species to isolate anything. And when I saw that, my first connection was with dihydroxylation with osmium. I thought, okay, maybe this is a nice way of converting an olefin into a diol. But then when I started to realize that he wasn't able, to isolate the cycloadduct between the nitrobenzene and the olefin, then I thought, okay, maybe this species is fragmenting like an ozonide, which is the intermediate of the reactions between ozone and an olefin, which is the key aspect of ozonolysis. And that made us really interested into this process because ozonolysis, is a unique reaction in organic synthesis. It's the only process that can cleave olefins in one step. It's a very powerful reaction, but everyone knows how difficult it is to run an ozonolysis just because you're dealing with explosive reagents.
How dangerous it is, yeah.
And then I thought, okay, maybe we can do something about it. And that took us 6 years to develop the process.
Fair.
So
that sounds about right.
In Manchester, very early on, we made all sorts of mistakes. But then eventually we did it, and I'm very proud of the project. Yeah.
It's super fascinating stuff, and like I mentioned, because I think now it's at a point where you were able to kind of capture the nitrogen doped ozonide. So now you could eventually, you could actually get to the 1,2 diol. And so it definitely is an alternative to.
Yeah, we have actually done that. Yeah.
Yeah. Yep. So now it actually is an alternative to osmium, right? Is it osmium? This dihydroxylation, I think, is the catalyst.
Hydroxide.
Yeah, it is. Yep. Which that is very toxic.
I think but it's not. The problem is that osmium. We have a non-toxic version of osmium, so you can use. So that's a great process. So it's a nice transition metal-free alternative, but it doesn't mirror, the power of osmium chemistry. We're far from that. I think the comparison with ozonolysis is more pertinent. I think when you think about ozonolysis and the reactions that we have developed, maybe not in terms of scalability, because on scale, of course, you cannot beat the use of a gas. Okay, but in terms of, for example, using ozonolysis in parallel screening, which is something that no one does because you cannot use ozone, on high throughput experimentation or reactions with very fragile functionalities, I think then it becomes a good alternative.
Yeah. Are you able to capture the endo ozonide? Like, are you able to capture that? And is that as like hazardous as like a primary or tertiary ozonide that you would get from ozonolysis? Or I don't know if you've like tried capturing those intermediates at all.
So capturing in which way? What do you mean?
The endoped ozonide, like I guess a 5-membered ring between like two carbons, and
Yeah.
then you have the nitrogen oxygen. Like, have you tried capturing those? Like,
Mm.
is that are you able to do that? Or is it kind of a fleeting
Sorry.
intermediate?
Yeah, so no, depending on the structure of the olefin and the substituents that you have, they can be very stable. So they
Okay.
normally crash out at the end of the reaction, and they're nice crystalline solids, and you can filter off, and you can put them in a vial and store in a fridge for a couple of weeks, which I think is very interesting because by replacing the central oxygen and doping it with this nitrogen and this aryl group, we go from something that is explosive to a stable chemical, effectively.
Yeah.
And now that we have stable species, I think is interesting because maybe there's many more reactions that we could subject the species to apart from the decomposition, which gives you the ozonolysis products.
Right. Yeah, I was curious about that because I know one of my group members, he's kind of doing ozonolysis right now to make like basically oxygen variants of adamantane. And it's like I don't really like to be around him when he's kind of doing those, when he has to set the oxygen tank and the ozonolysis instrument.
Yeah.
But there's definitely a huge advantage, right? I mean, because I know those primary ozonides are quite hazardous. You have to be very careful with them. You can't, you don't want to isolate those things. But it sounds like from what but the nitrogen variation of the ozonide sounds like like you mentioned, there's a crystalline solids. You can just kind of crush those. You can collect those and do whatever you want with them. So that's very useful then. The last thing I wanted to discuss with you is your most recent publication. Again, using those nitroarenes, but now you're gonna to make pyrrolidines. So kind of a different way of different transformation for the nitroarenes. I'd love to kind of pick your brain about how you guys came across this reaction. I know there's a lot of one of the big things in the community right now is atom interconversion. So being able to do nitrogen insertions, carbon deletions, things of that nature. So kind of taking fundamental building blocks and then transferring them into a different scaffold entirely is kind of really the direction a lot of organic chemists are going into now. So being able to take a nitroarene and to make a pyrrolidine is super, well, one, I think just really cool to look at the transformation, but perhaps synthetically useful to chemists. So I don't know if you want to tell us a little bit about that reaction.
Yeah, so that reaction is so when we started to work on this photoexcited nitroarene chemistry, we started to essentially think what else we could have done with those species. And one of the things that we discovered very quickly is that it was very simple using this method to convert them into singlet nitrines. And singlet nitrines are a very reactive species that people have studied from the 70s. Seeberger have done a lot of work with it. And people knew that if you could generate a singlet nitrine, the singlet nitrine tends to insert the nitrogen into the aromatic ring. Okay, so from 6 you go to 7. So you need to think in terms of the nitro group loses its 2 oxygen, and the nitrogen, which is a nitrine, gets into the aromatic ring. Okay, and then you form a 7-member ring. So people have done a lot of this chemistry in the past, especially using azides.
Yeah.
Because azides, you can decompose them photochemically very easily. They're very effective reagents. But with the nitro group, it was very difficult because you need to go at really high temperature, very forcing conditions, and then the methodology wasn't there to do that kind of transformations. So we started to work a lot into this area, and just because we were going from a 6-member ring aromatic to a 7-member ring, non-aromatic species. Okay, so we take something that is very stable and we convert it into something that energetically looks very unstable. Okay, and then another interesting aspect about this process is that you don't really destroy the carbon-carbon double bonds of the aromatic rings. They're still, some of them are still into the 7-member ring analog that you generate. And then one of the, let's say, most effective reactions that you can do with light are the electrocyclic reactions, where you can ring open and ring close cycles. Okay, and one of the key reactivity the only photochemistry can essentially do is the 4-pi electrocyclization reactions, which form 4-member rings. So then when we saw this kind of intermediates, we thought, well, we're using light to photoexcite the nitroarine. Maybe if we use the right light, we do the photochemical reaction, and then we do another photochemical reactions where we target these 2 double bonds that we have in these intermediates. And then we fold the molecule. So it's like, if you have to think in the way that we enlarge the molecule and then we fold it through. And then we generate all these sp3 stereogenic centers. We make these structurally rigid molecules. And then once that we started to see that the chemistry was working is when we saw an opportunity, because then we make molecules that have a very, let's say, rigid shape with a very nice convex and concave face. And then the 3D vectors, point in specific area of chemical space. And this is something that for the pharmaceutical sector is very useful, because sometimes you don't want fluxional molecules. You want molecules, that stay in one conformation. And sometimes you want that conformation not to, to be the one that is not the thermodynamically most stable one. So it's very difficult to get to this kind of molecules because the conformation will be frozen essentially.
Yeah.
And that's what made interesting that kind of chemistry, I guess. The fact that you take a feedstock that is flat, it's aromatic, so it's very stable. And then in 2 steps, the photochemical step, and then we need to do an hydrogenation. We convert it into a molecule which is not aromatic anymore. It's 3D and it's very compact in nature. And there's no synthesis for these types of building blocks.
I was going to ask, like, is this complementary in anything? But I doubt it. Like making a bicyclopyrrolidine, I doubt there's anything for it. So definitely probably synthetically useful for, definitely for like bioisosteres and trying different things. I think this would be
exactly. Yeah.
So yeah, I think as we kind of begin to wrap up here, are there, for your research group, are there kind of certain, where do you guys plan on? I mean, I probably don't want to give too much away, but like, where do you guys working for the future? Are there future projects you guys are trying to attack, or what can we look forward to from the Leonori group?
Yes. Yeah. So the nitroarenes, we're still very active on it. So we're still working a lot on this on these ideas of using nitrobenzenes essentially in completely different ways. We're still working on halogen-atom transfer and boron radical chemistry, which is something that we're very active at the moment. And also one of the things that we didn't discuss, but that I'm very excited about, is quantum tunneling, which is something that, again, I didn't know much about it, but we discovered very recently as part of an halogen-atom transfer process. And now it's really changed as well the way that my group is thinking about chemistry and the projects that we want to tackle. So we want to study a bit more quantum tunneling and these contributions to specific organic reactions. It's a big topic. There's a lot of people working on it, but it's something where I also want to go.
Yeah. I look for. Well, listen. There's no reason why I can't have guests come on for a second time. Hopefully, if in the future when you guys, we'll talk about some hydrogen tunneling, because that's a beast of a subject. I feel like though that's not a simple subject. Hydrogen tunneling.
Yes.
But Danielle, I want to thank you so much for coming on to the podcast today. It was extremely a pleasure talking with you and getting to hear kind of your chemistry firsthand. I think it's super, super useful, and to hear a little bit about yourself. I don't know if Milan play this weekend. I don't know if they're Coppa Italia or the Serie A this weekend, but hopefully Milan, the Serie A this weekend. I don't know who we playing this weekend. You know who we're playing?
Empoli.
To pull the schedule. We're playing Empoli this weekend. Well, I think they're in a relegation dogfight, so hopefully, AC Milan really should take care of business. My man's Christian Pulisic, the American. it's like such a
He's doing
great.
really well.
He's doing really well since it basically revived his career since being at Chelsea, where careers go to die at Chelsea.
Yeah.
But yeah, in any case, I want to thank you so much again for coming on, and
Thanks, Aidan.
we'll see you in the next one.
Thank you.